As you can see in the short clip, when we turn on a faucet, we can observe that the stream of water makes a circular jump on the flat surface of the sink. So we ask ourselves, how can we describe this behavior? We hypothesize that a hydraulic jump occurs due to the velocity of the fluid coming out of the faucet and surface tension between the fluid and the surface it is impacting. Our explanation is that when liquid at high velocity discharges into a zone of lower velocity, a rise occurs in the liquid surface. The rapidly flowing liquid is abruptly slowed and increases in height, converting some of the flow's kinetic energy into an increase in potential energy, with some energy lost through turbulence. The phenomenon is dependent upon the initial fluid speed. If the initial speed of the fluid is below the critical speed, then no jump is possible. For initial flow speeds which are not significantly above the critical speed, the transition appears as an undulating wave. In our example below displays how we found our initial and final velocity along with supercritical and subcritical Froude numbers. In our first step, we started off by solving for initial Froude number by using equation 1, which is derived from the conservation of momentum and energy continuity. Since the Froude number is greater than 1, we determined that the initial speed was supercritical. Then in our second step, we solved for initial velocity by plugging our calculated Froude number to equation 2, which relates to the velocity of the wave to the velocity of the fluid. Next, in our third step, we plugged in our calculated initial velocity to equation 3, which is the flow rate equation. For our fourth step, since we know the initial flow rate equals the final flow rate, we were able to use the Q value found in the previous step to find our second velocity. Lastly, for our fifth step, we plugged in our second velocity back into equation 1 to find our second Froude number, which was less than 1, indicating that it was a subcritical flow and a jump has occurred. The chart above relates the initial Froude number and ratio of heights to the description of the hydraulic jump. After our research, we concluded that the hydraulic jump is caused by a fluid transitioning from a supercritical velocity to a subcritical velocity. Flow must be above critical velocity to produce a hydraulic jump. A hydraulic jump can be observed when a flow transitions from a Froude number greater than 1 to a Froude number less than 1. A higher height and velocity would create a larger Froude number. To see a stable, well-balanced jump out of a faucet, you need a Froude number between 4.5 to 9.